Today we are going to take a look at a very simple way through which we can observe the different types of polarization of an electromagnetic wave. Now, to see this, we need two very simple and versatile available lab equipment. One is a function generator, the other is an analog oscilloscope. So, we are going to have this kind of a convention. The horizontal axis is my x-axis, the vertical axis is my y-axis, and the z-axis is coming out of the plane of this scope, and that is going to be the direction of traveling of the wave. So, I am going to show you how to observe a linearly polarized wave, to be very specific, a horizontally polarized wave. So, for that I am giving a 1 kilohertz sine wave into the X channel of an oscilloscope and observing it in the XY mode. So now that the signal is on, what I am seeing is a straight line segment on the horizontal x-axis. Now what this means? It means the wave is oscillating and traveling towards you. Rather, we can visualize it in this way. The electric field vector of this wave is oscillating along the x-axis and is moving towards you. Now, since the electric field vector is a function of the z-axis, you cannot see it varying because the z-axis is perpendicular to the plane of the oscilloscope screen. Now, to check whether the wave is actually oscillating or the field is actually oscillating, we can check that by reducing the frequency. Currently the frequency is 1 kilohertz, I will make it 1 hertz. You can see that there is an oscillation. This means the wave is such that the electric field vector is oscillating with a frequency of 1 hertz along the x-axis and traveling towards us. Now let us go back to our old frequency, which is 1 kilohertz. Now, this was horizontal linear polarization. We can check the same for vertical polarization. Now, I will simply connect the output of channel 2 of my function generator to the Y channel of my oscilloscope. Now, what I am seeing is the electric field vector is existing along the y-axis, but just like the previous case, it is still a function of z, and the wave is traveling along the z-axis. Again, we can verify by reducing the frequency. I am reducing it to 1 hertz. You can now observe the oscillation, that the electric field vector is oscillating at a frequency of 1 hertz and the wave is traveling perpendicular to the plane of the screen. So now I will go back to my old frequency, which was 1 kilohertz. Now, using a wave that is horizontally polarized and a wave that is vertically polarized, we can actually observe. What I will now do is that instead of activating one output, I will activate both outputs. Now what I am seeing is that there are two identical waves. One is horizontally polarized, the other is vertically polarized, which are applied to the two channels of my oscilloscope. Now those two waves act like two vectors, and what you are seeing right now is the resultant vector due to those oscillations. So now this is a linearly polarized wave whose electric field is basically oscillating 45 degrees angle with the x-axis and is traveling along the z-axis. The angle of this line can be changed by simply changing the voltage magnitude. So just to check that, I can make channel 1 something like 2 volts, which is less than right now. And what I am saying is that the tilt angle has essentially tilted towards the y-axis more, because the vertically polarized wave now has a higher amplitude as compared to the horizontally polarized component. So let me go back to the original voltage. Now let's suppose I am introducing a phase difference between the two components, the horizontal and the vertical. So suppose I decide to introduce a phase difference on channel 2 with respect to channel 1. So let's say I will give a phase difference of 30 degrees. Now what you are seeing is that the straight line has turned into an ellipse. What this means is, if you have two waves or two field components, one horizontally polarized and one vertically polarized, but there is a phase difference between them, in general the net wave will then be elliptically polarized. That means the electric field vector is oscillating along the trajectory of this ellipse, but the wave is still traveling along the z-axis, which is perpendicular to the plane of the scope display. So now we can check this effect little bit more in a better way by making this phase angle now 90 degrees. So when we make this 90 degrees phase difference between the vertically and the horizontally polarized components, this ellipse now turns into a circle. So therefore, this wave is now a circularly polarized wave. Now, as you may know, there are two kinds of circular polarization, or even elliptical polarization for that matter. One is a right-handed, the other is a left-handed. To take a closer look at the left-handed and right-handed polarizations, we can reduce our frequency and again apply the two same waves onto the x and y channel, but with a phase difference of 90 degrees, thereby having one vertically polarized wave or vertically polarized field and one horizontally polarized field onto the two axes, and introducing a phase difference of 90 degrees. Now what we are seeing is that if you are able to notice the way the beam is moving, it is moving counterclockwise. So it is like saying the curling of my fingers, if I am pointing towards the direction of rotation, my thumb is pointing outside. This is happening if I am using my right hand. So therefore, this is a right-handed circularly polarized wave. If you want to observe a left-handed circularly polarized wave, you need to essentially introduce a phase shift of minus 90 degrees. So doing that, we are now seeing that the beam is rotating clockwise. So if I am using my left hand and my thumb is pointing outside towards the direction of propagation of the wave, then this is a left-handed circularly polarized wave. Please note that the polarization has nothing to do with the direction of traveling of the wave. For all the cases that we have seen, the wave is still traveling along the z-axis, that is the direction perpendicular to the surface of the screen. It is only the electric field vector that is rotating as a function of time or moving as a function of time. This is due to oscillations of the electric field components on the individual x and y axis. The equipment that you see over here is called as a spectrum analyzer. It is connected to this dipole antenna, which is, as we discussed, is going to behave as a receiving antenna. Now a spectrum analyzer is no big deal. It will essentially show you the signal that is being received, but in the frequency domain, right? So if I am receiving a sine wave, it should show me a single spike as per Fourier theory. So now what I am going to do is I am simply going to switch on the transmitting antenna, which will transmit a signal of frequency 900 megahertz, and then we are going to see whether our receiving antenna is able to catch it or not. So if you notice here very carefully, there is indeed a spike that is coming. This spike corresponds to the sine wave that is being generated and transmitted via this transmitting antenna, which we saw earlier, and is being received by the dipole. Now, if I simply change the axis of polarization of the dipole, let us see what happens. Now, instead of making the dipole vertically polarized, I am now going to make it horizontally polarized. And you can now see that the signal is much more weak as compared to the previous case. This just shows that vertical polarization and horizontal polarization are two orthogonal states of polarization, and therefore they cannot work together as far as transmission and reception of the signals are concerned. Thank you.